Welcome to the Deep Dive. Today we are diving headfirst into some pretty dense research, really focusing on solving a major technical hurdle in AI.
Yeah, really tough one.
Specifically, how do you get AI to generate videos that are long, look great, and let you interact with them, in real time?
That's basically the holy grail for generative media right now. And when we say interactivity, we mean the user can actually feed it new text prompts while it's running.
Like changing the story on the fly.
Exactly. Guiding the narrative, switching the subject midstream, and needing it to respond instantly and stay coherent over long stretches. That's been the big bottleneck holding things back.
So the framework we're digging into from the sources, it's called LongLive. It's a new kind of architecture, frame-level autoregressive, or AR, and its whole mission seems to be breaking that trade-off.
Right, the classic speed versus quality problem.
Yeah, right.
And you really have to understand this trade-off. Most of the really high-quality video models out there today, they're based on diffusion, fantastic detail, visually stunning sometimes, but
Painfully slow.
exactly, latency nightmares, they just can't keep up the speed you need for real interaction or, super long videos.
Okay, so if diffusion's too slow, the alternative is usually these causal AR models. They're faster.
They are faster, yes, but then you hit the other wall, quality degradation. The longer they generate, the more the video kind of drifts, loses visual consistency, things start looking weird.
So LongLive claims to fix this. What's the headline number? What made you guys take notice?
Well, the metric that really jumps out is the speed comparison. You take a baseline, something like Skyreel's V2, which uses diffusion forcing. It clocks in at about 0.49 frames per second. Half a frame a second.
Oof.
LongLive, using this new architecture, it sustains 20.7 FPS on just one NVIDIA H100 GPU.
20.7. That's a massive leap.
It's huge, and that speed enables stable generation for videos up to 240 seconds long, 4 minutes.
Wow. Okay, let's definitely unpack this. Going from less than half a frame per second to over 20, that requires some serious academic rigor in how they designed it. Let's start with the basics. Why was that diffusion baseline so incredibly slow?
It really boils down to attention mechanisms and memory management. Diffusion models and these diffusion-forcing variants, they rely heavily on something called bidirectional attention.
Bidirectional meaning
Yeah.
it looks both ways, past and future frames.
Exactly. It considers every frame in relation to every other frame within a certain window, both before and after, to make sure everything is perfectly coherent in that short clip.
And that bidirectional need, that's the killer for speed, isn't it? Because it stops you using that common optimization trick.
Precisely. It prevents the use of key value caching or KV caching. That's a standard technique for speeding up sequential models, like, large language models for text.
Right.
If the model has to constantly look both backward and potentially forward, it can't just reuse past computations easily. It has to recompute a lot of the context for every single new frame.
Which leads to tons of redundant calculation.
Massive amounts. The sources actually benchmarked this, generating just a 60-second video using that diffusion forcing approach. It took about 50 minutes. On a top-tier H100 GPU.
50 minutes to make 1 minute of video. Okay, yeah, that's completely impractical for anything interactive.
So the AR models then, they can use KV caching because they only look backward causally.
Great.
They run faster, but then they have that consistency problem, the drift you mentioned. What's the root cause of that? Why do they degrade?
It's mostly down to a mismatch between how they're trained and how they're used. It's often called the train short, test long problem.
Train short, test long, meaning?
Meaning training these models on videos that are minutes long is just computationally way too expensive.
Yeah.
So typically they're only trained on short, clean video clips, maybe a few seconds.
Okay.
But then at inference time, when you actually use the model, you ask it to generate maybe a 2-minute or even 4-minute video. And to do that, it has to make predictions based on its own previous predictions. So it's conditioning on frames that it generated itself, which might not be perfect.
Exactly. It's conditioning on this long history of self-generated, potentially slightly imperfect, slightly noisy frames. But it was never trained to handle that kind of long accumulated imperfection.
It's like that game of telephone, right? The message gets garbled down the line. Here, the visual story just gets noisier and less consistent frame by frame.
That's a good analogy. Errors accumulate, the scene starts to drift, characters might change appearance. It breaks down.
And as if that wasn't hard enough, then you throw in the demand for real-time interactivity. The user wants to suddenly change the prompt.
Right. You're generating a dog chasing a ball in a park, and suddenly the prompt switches to the dog is now riding a skateboard. The model has to adapt instantly, semantically, but keep the visual flow smooth.
That transition. Visually smooth, but semantically instant. That sounds incredibly difficult. LongLive needed a really smart fix for this. The paper discusses two sort of naive ways to handle it, and both fail pretty badly.
They really do. Let's say the prompt changes. Option 1, you just clear the entire KV cache, wipe the slate clean.
Okay, what happens then?
Well, the model immediately picks up the new prompt, the new semantics, so adherence is great, but
The video jumps.
completely. You lose all temporal continuity, the motion gets choppy, the scene might abruptly reset. It's visually jarring because you've erased all the memory of what just happened.
Okay, so clearing is bad for smoothness. What about option 2? Just keep the existing KV cache, don't clear it.
If you retain the cache, you do keep the smooth visual continuity, which is good. But the cache is still full of information related to the old prompt.
Ah, so it doesn't react to the new prompt properly.
Exactly. The model shows what the researchers call prompt inertia. It's like it's stuck on the old idea. It either ignores the new prompt for a while or adapts really, really slowly. There's a lag.
So you get smoothness, but lose responsiveness. Neither is good.
Neither works for true interaction.
So LongLive introduces this KV-recache mechanism. How does that thread the needle? How does it get both smoothness and instant switching without adding a ton of latency?
It's quite clever. Right at the moment the prompt switches, LongLive performs a very specific partial recomputation of the cache. It's based on a key insight.
Which is?
That the information needed for visual continuity, the motion, the scene layout, is primarily encoded in the video frames the model has already generated. But the semantic guidance, the what's happening, comes from the prompt embeddings.
Okay, so it separates those two things.
Precisely. So at that boundary point, it recomputes the KV cache. It uses the history of generated video frames to preserve the visual state, the motion cues. But crucially, it pairs that visual context only with the embeddings from the new prompt.
I think I follow. So it keeps the visual memory, but swaps out the old meaning for the new meaning in the cache.
That's a great way to put it. The resulting cache still has all the cues for temporal continuity from the video history, but semantically, it's completely aligned with the active new prompt instantly.
And the results showed this worked much better.
Significantly better. Their ablation studies showed KV-recache achieved superior subject consistency, background consistency, and also better semantic adherence, which they measured with CLA score, compared to both clearing the cache and retaining the old cache.
Okay, that handles the interactive switching part. But what about the underlying problem of drift during long generation, even when the prompt isn't changing? That train short, test long issue. How did LongLive address that fundamental error accumulation?
They tackled it head-on with a different training approach. They call it streaming long tuning. The goal was to enforce a true train long, test long setup.
Train long, test long. So actually train it on longer videos.
Yes. They specifically trained the model to generate long sequences up to 60 seconds in their training runs, and critically, they forced it to condition on its own, potentially imperfect predictions during that long training rollout.
Just like it has to during actual use during inference?
Exactly. By exposing the model to this long-term self-generated context during training, it learns how to handle it. It learns to mitigate those consistency breaks and control the error accumulation over time.
But training on 60-second clips? Isn't that incredibly computationally expensive? That sounds like where you'd run into massive memory problems, those out-of-memory errors or OOMs.
It would be if you did it naively, but the streaming part of streaming long tuning is how they make it efficient.
How does the streaming work?
To avoid running out of memory, they detach the computational graph for frames generated earlier in the sequence. So after generating, say, a 5-second chunk, they effectively freeze those past frames in terms of backpropagation.
So the memory needed doesn't keep growing with the video length.
Right. The memory use stays limited, roughly proportional to the size of the current short clip window they're processing, like that 5-second chunk. And gradients are only calculated for the newly generated section. It's a smart trick.
That does sound efficient. How efficient was it in practice?
Remarkably so for this kind of task. They reported fine-tuning their 1.3 billion parameter model for this minute-long generation capability using just 32 GPU days. That's very resource-friendly for achieving this level of long-term consistency tuning.
Okay, that's impressive. So better training handles long-term consistency. Now let's circle back to speed. Getting that 20.7 FPS number, this is where it gets really interesting, right? They needed specific inference time optimizations too.
Absolutely. Training helps consistency, but you still need raw speed for real-time generation. They use two main techniques for efficient inference. The first one is pretty intuitive. Short window attention.
Short window attention, meaning the model doesn't look back at the entire video history when generating the next frame.
Exactly. We know attention computation scales typically quadratically with the length of the sequence you're attending to. So attending to a full 60-second or 240-second history is just too slow.
So they limit how far back it looks.
Yes. They implement short window attention, where the model only performs attention calculations over a small, fixed window of recent history, say, just the last 9 latent frames, instead of potentially hundreds.
And that drastically cuts down computation and memory.
Massively. The complexity now scales with that small window size, not the total video length. Big speed up.
Wait, if you only look back 9 frames, don't you lose the long-range consistency you just worked so hard to train for? How does the model remember what the character looked like 30 seconds ago or what the background scene is if its memory window is that short?
That's the critical trade-off, and that's where the second mechanism comes in, which I think is the real aha moment here. The frame sync.
The frame sync. Okay, what does that do?
It's a clever way to retain long-range information without paying the computational cost of a long attention window. What they do is they take the very first few frames generated, for example, the initial 3 latent frames, and designate them as persistent global sync tokens.
Persistent global sync tokens, meaning these first few frames are special.
Very special. They are never evicted from the KV-recache as the generation window slides forward. They are permanently kept.
So they always stay in the model's short-term memory, effectively.
Precisely. In every subsequent attention calculation, these fixed sync tokens representing the initial state are concatenated into the attention context, along with the recent local tokens, the 9-frame window.
Ah, I see. So these sync tokens act like permanent anchors, global reference points for the whole scene.
Exactly that. They serve as global anchors, carrying information about the overall scene semantics, maybe the main character's identity, the background setting, things established right at the start. It's like the model constantly has a little thumbnail sketch of frame 0 to refer back to, keeping it grounded even when its main focus is only on the immediate past.
That combination is really elegant. You get the speed from the short local window, but you retain the long-term consistency thanks to these anchored sync tokens.
It's a very effective compromise. The research showed that this specific setup they tested, a 9 local frame window plus 3 sync tokens, achieved long-range consistency quality that was close to using a much slower, full 21-frame attention window.
And the efficiency gains were significant.
Absolutely. This short window plus sync combination resulted in a 28% reduction in the total end-to-end compute time and a 17% reduction in peak memory usage compared to just using a longer window. That efficiency boost was key to hitting that 20.7 FPS figure.
So pulling it all together, what does this long-live framework really signify for, the future of AI video?
Well, it demonstrates a practical path towards real-time, long-form, and interactive video generation. It did this by systematically identifying and solving the 3 main roadblocks we discussed.
Right. Efficiency, which they got through the AR architecture combined with short window attention and the frame sync.
Yep. Then long-term consistency, solved by that streaming long tuning method.
And finally, the interactivity, the prompt switching, handled by the KV-recache mechanism.
Exactly. It's a suite of solutions working together.
And the performance metrics really underscore the success. Let's just recap those numbers for everyone listening.
Sure. Sustained 20.7 FPS on an H100. Stable video generation up to 240 seconds, which is 4 minutes.
Impressive.
And they also showed it works well with INT8 quantization that's reducing the model's numerical precision, which shrank the model size from 2.7 GigaB down to just 1.4 GigaB, with apparently minimal impact on quality.
Which makes it much more practical to actually deploy.
Absolutely. This looks like a very efficient and potentially deployable architecture for building next-gen creative tools.
What strikes me is the technical elegance. It feels like they achieve this not just by throwing more parameters or data at the problem, but through really smart architectural and training innovations. What's the big takeaway for people working on scaling up AI content generation?
For me, the most profound finding, sort of hidden in the details, is this link between training methodology and inference efficiency. They found that tuning on long videos wasn't just about making long videos look better.
It was more fundamental.
Yes, it was actually a prerequisite for successfully unlocking the most aggressive inference speedups, like that short window attention combined with the frame sync. Those speed hacks only really work well if the model has already been trained to maintain consistency over long durations.
Interesting. So the training enables the efficiency trick.
It seems so, and this raises a really interesting question for the field, I think. As we try to scale AI content generation, are the biggest breakthroughs going to come from just making models bigger and bigger? Or are they going to come from clever fine-tuning methods like this? Methods that really align how the model is trained with how it needs to perform efficiently at inference time.
A shift from brute force scaling to smarter, more targeted training regimes.
Maybe. And it makes you wonder what other architectural optimizations or efficiency tricks might only become possible once we start training models on even more complex, truly long-form, maybe even interactive context from the beginning.
That's a great point to ponder. Where do the real performance gains lie in the future? Definitely something for our listeners to think about. Well, that brings us to the end of this deep dive into the LongLive framework. Fascinating stuff.
It really is a significant step forward.
Thank you for joining us, and we'll catch you on the next deep dive.
What if you could generate long, high-quality videos with AI, but not by waiting around for minutes or even hours, but in real time? And what if you could actually interact with it? Change the story on the fly, just like a director. Well, it looks like that future just took a massive leap forward. So get this. This entire scene of Iron Man in a war-torn city, it's not from a movie, it's not from a video game, it's being generated live by an AI. The user kicks things off with a simple prompt. Iron Man walks toward the camera through a war-torn, crumbling city at dusk. And just like that, the scene starts to unfold. But here's where it gets absolutely incredible. The user decides, you know what, let's change the story. They type in a new prompt. The enemy fires emerald green energy beams at him, and instantly the video responds. The whole scene is filled with these energy blasts, and it does it all while keeping everything visually consistent. This is real-time interaction. But they're not done yet. They decide Iron Man needs to fight back. So, new prompt. Iron Man powers up, his chest arc reactor unleashes a colossal blue beam. And just like that, boom, the scene evolves again right before your eyes. This is a new framework called LongLive, and it's basically turning video generation into a live, creative conversation. Okay, so let's dive into the research that makes all this possible. We're going to start with the big problem LongLive is trying to solve, then we'll see how it works under the hood, we'll look at the results, and finally, we'll explore what this all means for the future of, well, creating stuff. Now, that demo might look like pure magic, but the technical reality of generating long, high-quality, and interactive video has been this huge challenge. It's kind of a classic problem in AI research. You can get quality, or you can get speed, or you can get length, but getting all three at once has been, well, almost impossible. And here's the heart of the problem. On one hand, you've got diffusion models. They make absolutely beautiful, high-quality video, but they are incredibly slow, and you can't really interact with them. Then, on the other hand, you have autoregressive models, or AR models. They're super fast, they can be interactive, but the quality, it just tends to fall apart over longer videos. So you've been forced to choose. Do you want beauty, or do you want speed? This chart just illustrates that speed problem perfectly. Look at diffusion models, crawling along at half a frame per second. You'd be waiting almost 2 minutes just to generate 1 second of video. The faster AR models are way better for sure, but LongLive pushes that boundary even further, hitting over 20 frames per second. That is true real-time performance. So, how does this new framework, LongLive, actually solve this dilemma? The key insight here is that it's not about choosing between quality and speed. It's about building a system from the ground up that's designed to deliver both. So what is LongLive exactly? Okay, at its core, it's a frame-level autoregressive framework. All that means is it generates video 1 frame at a time, based on the ones that came before it, which is the key to being so fast. But it mixes in some brand new techniques specifically designed to keep that quality high over long videos and, this is the crucial part, handle your interactive commands without losing its train of thought. Okay, so how does it actually pull this off? This is where we get into the real academic core of the paper.
On LongLive's success really comes down to three key technical innovations that all work together to achieve what other models just couldn't.
And these are the three pillars. First, there's something called KV-recache, which is the secret sauce for that seamless interactivity. Second is streaming long tuning, and that's what solves the quality problem. And third, efficient inference, which is how it gets that blistering real-time speed. Let's break each one down. So this first pillar, KV-recache, it tackles that interactivity problem head-on, right? I mean, when you give it a new prompt in the middle of a video, how does the AI smoothly switch gears without making a jarring cut or just ignoring you completely? That's the problem this solves. And what's really cool about this slide is you can see the difference directly. On the left, without this technique, changing the prompt is a mess. You either get this ugly hard cut or the model just keeps doing what it was doing. But look on the right. LongLive uses KV-recache to cleverly refresh its memory. It keeps all the visual info from the past frames, but it injects the meaning of your new prompt, and the result is a perfectly smooth, coherent transition.
The second pillar takes on the quality problem. So why do other fast models tend to get glitchy and weird over time? Well, it's because of a mismatch. They're trained on short little clips, but then we ask them to generate long ones. LongLive fixes this with a really smart method called streaming long tuning.
And the idea here is actually brilliantly simple. The old way, train short, test long, that's like practicing for a marathon by only running 100-meter sprints. Small errors just pile up, and eventually you're going to fall apart. But LongLive's solution is train long, test long. During training, the model is actually forced to generate really long sequences and learn from its own outputs, imperfections and all. This makes it incredibly tough and able to keep that quality high for way longer.
And the final pillar, this one is all about speed. Because having quality and interactivity is great, but if it's not fast enough for a person to use it live, it kind of loses all its magic. So efficient inference is how LongLive gets that real-time performance.
See, traditionally, for an AI to stay consistent, it needs a pretty big attention window. It has to look back at a lot of previous frames to figure out what to do next. And as you can see from this chart, the bigger that window is, the better the consistency. But that comes at a huge cost to speed and memory. It just slows everything down.
So, the crucial point here is that LongLive uses this really clever combination of tricks. It uses a very small, very efficient attention window, only looking at the most recent frames. But, and this is the genius part, it creates what's called a frame sync. It basically anchors the very first frame in its memory forever. This one single anchor point gives it a constant reference, which gives it the long-range consistency of a huge window, but with the speed of a tiny one.
Okay, all of this theory sounds pretty impressive, but does it actually work in practice? Now for the proof. Let's look at the hard numbers from the paper, where they benchmarked LongLive against other top models.
This table tells a really clear story. On 30-second videos, LongLive gets the highest total quality score. But look at the throughput column. At 20.7 frames per second, it's not just a little faster, it's over 40 times faster than a high-quality model like Skyreel's V2. It is genuinely the best of both worlds.
And it's not just about machine scores either. When they asked actual people to compare the videos side by side, the preference was overwhelming. Over 54% of users said they preferred the overall quality of LongLive's videos. That's nearly double its closest competitor. People can really see the difference.
So, we've looked at the problem, we've looked at the technical solution, and the results are pretty impressive. So let's zoom out now and just think about what a technology like this really means for the future.
What we're looking at here is not just another research paper. It's really a foundational step toward a whole new way of creating content. It's about moving away from static, one-and-done generation to a process that's dynamic, interactive, and collaborative between a person and a machine. This could honestly democratize filmmaking, animation, and storytelling in ways we're only just starting to wrap our heads around.
And that leaves us with one final, kind of provocative thought. For centuries, bringing complex visual stories to life required massive resources, deep technical skill, and huge teams of people. With tools like LongLive becoming more powerful and accessible, the main barrier isn't going to be budget or technology anymore. It's just going to be imagination. What new worlds, what new stories will emerge when anyone can have an entire film studio right at their fingertips?